I will share the slides in few minutes. Hope the slides is visible. So good evening all. Welcome to week 7 assignment solving session of the course Introductory Organic Chemistry 2 August 2024 to October 2024 by Professor Harina Chakrapani and Professor Neeraja Deshaputre. Myself Anisha Suresh, PMRF TA for this course from IIT Bombay. So coming to the summary of the week 7. So in this week, the topics that were discussed were conjugate addition. We have discussed in detail regarding 1-2 addition and 1-4 addition, followed by the formation of kinetic and thermodynamic products and the differences between hard and soft nucleophiles. Following this, enol and enolate alkylation reactions have been discussed, and the regioselectivity of these alkylation reactions have been discussed. And finally, acylation of enols or enolates and the related name reactions have been discussed. So coming to conjugate addition, that is 1-2 addition and 1-4 addition. So if we are having this compound in hand, and if we are treating it with sodium cyanide in the presence of HCN at 5 to 10 degrees Celsius, that is low temperature, we are getting this addition to the carbonyl, that is 1-2 addition reaction. And when the same compound, if we are treating with NaCN and HCN, the only difference that is made here is the temperature is 80 degrees Celsius, that is little higher temperature. So we are getting this conjugate addition product, that is 1-4 addition. So why this is happening? So this can be discussed based on the molecular orbital pictures. So based on the molecular orbital, so this is butadiene, and if we are replacing one of the carbon with oxygen, we will get acrolein, which is a 1,4 addition precursor. So here butadiene, the molecular orbitals will be as such. This is psi 1, psi 2 with one node, psi 3 and psi 4. So here there is only one node, as you can see here. Here there will be two nodes. Here three nodes. So since this is having 4 electrons, this, psi 2 is the highest occupied molecular orbital, and LUMO, psi 3 will be the LUMO, that is lowest unoccupied molecular orbital. And when we come to acrolein, because of the electronegativity of this oxygen, the energy of this molecular orbitals have come down. And when we see the LUMO, we can understand that this carbon, that is the 1-4 addition position, that is the conjugate addition position, it is having a larger lobe. So when the nucleophile is coming, it can um, overlap with this larger lobe of this carbonyl, and thus form this new sigma bond. Okay. So by when we are considering orbital contribution, then 1-4 addition might be favored. Now coming to kinetic and thermodynamic control. So we have seen we are having this product. When Cn minus C is added and the reaction is fast but reversible, it can lead to formation of this kinetic product, that is the cyanohydrin. This kinetic product is what means the product that will form faster is known as a kinetic product. So this reaction will take place at a faster rate, but the reaction will be reversible. And when this reaction is carried out at a slow rate, we will get this irreversible conjugate addition product. So this thermodynamic addition product will be more stable. So talking about the kinetic and thermodynamic control, the product that forms faster, it is known as a kinetic product, and the product that is more stable, it is known as a thermodynamic product. So forms faster, kinetic product; more stable, thermodynamic product. So the conditions that we use for giving rise to the kinetic product is known as kinetic control, and the conditions that give rise to thermodynamic product, they are known as the thermodynamic control. So why we are calling this kinetic product and thermodynamic product? The reason we will be discussing here. So the attack can take place at this position or this position. Since this lobe is more when we are considering orbital contribution, so this addition will be more favored. And when electrostatic attraction is considered, so this position will be more favored for addition. Okay, when we are considering charge or electrostatic condition, then 1 2 addition will be taking place. When we are considering orbital contribution, then 1 4 addition can take place. So when this 1 2 addition is taking place, that means here this carbon oxygen double bond is breaking, so loose of C double bond or pi bond, which is having an energy of 369 kilojoule per mole, and the new bond that is formed is this carbon between carbon and Cn. And when we consider this 1 4 addition, here the C double bond C bond is breaking. C loss of a C double bond C pi bond is taking place with an energy of 280 kilojoule per mole. And here the CCN, CC sigma bond is forming. So in both cases, the gain of CC sigma bond is taking place. And when we consider the loose, here an energy of 369 kilojoule per mole is needed. And here for the breaking of the C double bond C bond, we require 280 kilojoule per mole. So this is requiring more energy contribution, so this is less stable or less favored, and this will be more favored when we are considering the energy contribution. So that is why this is known as a thermodynamic product and this is known as a kinetic product. Now coming to hard and soft nucleophiles. So these are some examples of hard nucleophiles. So when we are considering hard nucleophiles, they should have more charge, and size should be less. And when we are considering soft nucleophiles, their size should be larger and charge should be diffused. And something that falls between these two, they are known as borderline nucleophiles. So some examples of hard nucleophiles are F minus, OH minus, OR minus, Cl minus, etc., SO2 minus, etc., and some others Grignard reagents, alkyl lithiums, etc., will fall under hard nucleophiles. And coming to soft nucleophiles, I minus, rs minus, rsc minus, s2 minus, etc., then alkenes, this phosphines, pphd sort of nucleophiles, aromatic rings, they will fall under soft nucleophiles. And this n3 minus, cn minus, rnh2, r dash nh, br minus, they will fall in the borderline. So, for reactivity of hard and soft nucleophiles, the reactions of hard species are dominated by charges and electrostatic effects, and the reactions of species are dominated by orbital effects. Then hard nucleophiles tend to react well with hard electrophiles, and soft nucleophiles tend to react with soft electrophiles. So hard nucleophiles will react at hard centers and soft nucleophile will react at soft centers. So we have seen that this hard species, they are dominated by charges and electrostatic effects, so it can do 1 2 addition reactions. As we have seen, this position, that is this position is dominated by electrostatic attraction or charges, and here this 1 4 position is dominated by orbital interactions. So the soft nucleophiles can undergo 1 4 addition reaction at a faster rate. Now, so here we can say hard nucleophiles tend to react at the carbonyl carbon which is a hard electrophile of an enol, and the soft nucleophiles tend to react at the beta carbon, that is the 1,4 position, soft of an enol, and lead to conjugate addition. Now coming to alkylation reaction of enols and enolates. So this is how an enolate ion is getting formed. When we are using a stronger base, the complete formation of anion can take place and it can lead to formation of this enolate. And when we are using a weaker base, the anion can be in equilibrium with the starting material. So the base will abstract this alpha proton and it will lead to formation of this enolate. And once this O minus will fall, this carbon carbon double bond will go and attack on this alkyl halide in an SN2 fashion, leading to formation of this uh, desired compound. So first formation of enolate anion will take place, and second alkylation reaction will take place by SN2 reaction with alkyl halide. Now coming to alkylation of aldehydes. So this reactions with normal enolate formation reactions with aldehydes are not favored, as there can be side reactions. So reactions which compete with aldehyde enolate formation. So here when we are using this LDA, this is lithium diisopropyl amine, so it can lead to formation of uh, enolate first, lithium enolate first, and it will undergo self condensation instead of the alkylation reaction to take place. So here this self condensation is also a side reaction that is taking place, and also this LDA, it can act as a nucleophile. LDA is non-nucleophilic, but some other bases if we are using, it can undergo nucleophilic addition with the carbonyl and lead to give this products. So avoid using lithium enolates of aldehyde. So how we will do alkylation reaction of aldehydes? For that we can use different methods. For aldehyde alkylation, one general best solution is the use of acyl-enolates. Acyl-enolates are the best general solution for alkylating aldehydes with most electrophiles. So with very SN2 reactive alkylating agents, we can use enamines, and with the very SN1 reactive alkylating agents, we can use silyl ethers. Because in the case of silyl ethers, we are using TiCl4 as a Lewis acid. It can coordinate with the alkyl halides and it will lead to formation of the carbocation. Now coming to regioselectivity. So the if there are two alpha hydrogens possible, it can lead to formation of the kinetic enolate and it can lead to formation of the thermodynamic enolate. So if we are abstracting this proton, it can lead to formation of kinetic enolate. So when we are considering a normal alkene, if it is less substituted alkene will be less stable compared to more substituted alkene. So this thermodynamic enolate will be more stable, hence it should be more substituted enolate. This will be less stable. So similar to alkenes, we are considering this kinetic enolate and thermodynamic enolate. So the kinetic enolates are less substituted, they are less stable. So it is favored by strong hindered base. So if it is a hindered base, it cannot abstract this proton because of steric reasons. Hence this formation of the kinetic enolate will be favored when we are using a strong hindered base. And we should follow low temperature and short reaction time for the formation of kinetic enolates. And when it comes to thermodynamic enolates, it will be more substituted enolates and it is more stable. So for this reaction to take place, we should use an excess of ketone or this this excess of ketone, and a high temperature and long reaction time is required for the formation of the thermodynamic enolate. Now, for the acylation reaction to take place, we have seen many name reactions in the last video of this module. So, in that, they have discussed regarding the Claisen ester condensation. So, this is the mechanism for Claisen ester condensation. So, we are having an ester having an alpha hydrogen. So, in the presence of the base, this alpha hydrogen will be abstracted, leading to formation of the enolate. And once this is falling back, this carbon carbon double bond can attack on the ester, leading to formation of this tetrahedral intermediate. And once this O minus will fall, this OET gets removed and it will lead to formation of this uh, desired compound. So this is Claisen ester condensation. So this is also similar to aldol condensation reaction, and there will be one more proton here. So that upon abstraction will lead to formation of enolate, thus making this reaction irreversible. Okay, and when this instead of the same molecule, if you are using two different esters, then it is known as crossed Claisen ester condensation. So this will be formed. So again, this proton can be abstracted. So this is stable delocalized enolate. So this step makes the reaction irreversible. So in all the steps, the reaction is reversible. So this step makes the reaction irreversible, and upon workup, we will get the desired product. 3-oxo ester or beta keto ester. Now coming to Stobbe condensation, so we are having a ketone and a diester. So this diester, it can lead to formation of the enolate and in the presence of a base, and it can add on to this carbonyl carbon of the ketone, leading to formation of this tetrahedral intermediate. Now this alkoxide O minus can add on to this ester, lead to formation of this tetrahedral intermediate, and once it is falling back, this OET will get removed, leading to formation of this lactone, and then even CB sort of mechanism. This proton will be abstracted, leading to formation of a carbon-carbon double bond, and this uh, carbon-oxygen bond will break, leading to formation of CO2 minus. So this will be the final product. So this reaction is known as Tobbe condensation. Now coming to Novanangel condensation. So here we are using a amine. So this amine will be acting as a base. It will abstract the proton, and that enolate or that anion will add on to the carbonyl carbon. A nucleophilic addition reaction will take place, leading to formation of this intermediate, and then even CB sort of elimination reaction will take place, leading to formation of this alkene, and regenerating this amine, and water will be the byproduct. Now coming to Darson's glycidic ester synthesis. So in this we will be having a alpha chloroester. So the base will abstract this proton, leading to formation of this enolate, and this enolate can go and add on to this ketone, leading to formation of this uh, tetras, tetrahedral intermediate, and this O minus can undergo an SN2 reaction at this position, eliminating this chloride, leading to formation of this epoxide. So this is known as Darson's glycidic ester synthesis. And benzoin condensation was also discussed, where we will be having a benzaldehyde, and Cn minus will add on to this, leading to formation of this tetrahedral intermediate, and then the base will abstract this proton, leading to formation of this nitrile enolate. So this nitrile enolate will be forming. So this will be a nucleophilic carbon, and when this N minus is falling down, this carbon carbon double bond will go and attack on other molecule of benzaldehyde, leading to formation of this intermediate, and this for the regeneration of this carbonyl. So this proton will be abstracted, and once it is falling back, Cn minus will be removing, and we will get this final product. So this is benzoin condensation. And apart from this, other name reactions that were discussed were Diekman reaction, Robinson annulation, Henry reaction, Stoke-Enamine reaction. So these mechanisms we will see in the slides when we are doing problem solving. So for references, you can follow Claydon Organic Chemistry Chapter 10, Chapter 26, Chapter 28, and Chapter 29. So now coming to question number 1. So identify the intermediate X and the final product Y in the following sequence. So we are having this alpha beta unsaturated ketone, and it is treated with LDA at minus 78 degrees Celsius and treated with methyl iodide and then quenched with water. So we will get an X, and then that product is treated with thiophenol in the presence of triethylamine, and we will get Y. So what is X and what is Y? So we are given four options, out of which what is the right option? Option D. Yeah, it is the right answer. So we will see the mechanism. So this is our starting material. When we are treating it with LDA, so this proton LDA, that is lithium diisopropyl amine, it will abstract this proton, leading to formation of this lithium enolate. And this, once upon falling back, it can go and attack on this methyl iodide in SN2 fashion, leading to formation of leading to alkylation at the center. And this, upon quenching, it will lead to formation of X. Now we are having X in hand, and we are treating it with pH thiophenol in the presence of triethylamine. So triethylamine can abstract the proton on this thiophenol, and it will lead to formation of pH S minus. So we have seen this is a soft nucleophile. pH S minus is a soft nucleophile. So it will undergo conjugate addition reaction at this position, and we will get this intermediate. And this can abstract, this will undergo protonation, leading to formation of this final product Y. Is the mechanism clear? Here what we should remember is that this thiophenol is a soft nucleophile, that is why 1,4 addition reaction is taking place. Soft nucleophile, it will undergo conjugate addition. So the right answer is option D. Now coming to question number 2. The scheme below outlines a mechanism for the synthesis of a ketone from ethyl 3-oxo butanoate and acetoacetic ester ketone synthesis. In which state do the curly arrows wrongly show the flow of electrons? Predict the structure of the enolate formed in the given reaction. So they are asking, in which stage do the curly arrows wrongly show the flow of electrons? So please go through this mechanism, and please and tell at which step the arrow pushing mechanism is wrong. Stage 4. Yeah. So we can see here they have shown this is correct. This is decarboxylation is correct, and here then this tautomerism step. So here the right mechanism will be like this. This will abstract the proton in this fashion and form O minus. Right. This is proton. It is H plus. As shown here, they are showing like H minus. So whatever mechanism they have shown here is wrong. So stage 4 mechanism is wrong. So the arrow pushing in stage 4 is wrong. Is it clear? Okay. Now coming to question number 3. Which is the main product of the following reaction? So what is the name reaction here?
Diekmann
Claisen,
condensation.
Claisen condensation.
The Claisen condensation is right, but when two esters are uh, present and intramolecular reaction is taking place, that is specifically known as Diekmann condensation.
Hickman.
So here what is the main product that is formed?
D.
Yeah, 2 is the right answer. So we will see the mechanism. So this is our starting material. So in the presence of a base like NaOET, so OET minus will be acting as a base. It can abstract this proton, lead to formation of this enolate, and this O minus will fall back, and this carbon-carbon double bond will go and attack on this ester, so leading to formation of this tetrahedral intermediate. And this upon falling back, this OET will get removed, and we will get this product. And one more, so for making this reaction irreversible, so this OET can abstract the proton again and lead to formation of the enolate. This upon workup will give this this upon workup we will get this as the major product. Clear? So this is the condensation. So this is the major product that we are getting now.
Ma'am,
Yeah.
in second, there is condition hydrolysis. Whether this ester will undergo hydrolysis to give carboxylic or not.
No, no, it will not. It is acid mediated now. If it is base mediated condition, then ester can, like NaOH condition or LiOH condition, then ester can undergo hydrolysis and give OH. Here just proton abstraction will take place in H3O plus condition. Okay.
Okay, ma'am.
Now coming to question number 4. The major product formed in the following reaction is, a 1,3 dicarbonyl compound is there, and this alpha beta unsaturated compound is there, and it is treated with base in alcohols, as a solvent. So what we will get as a major product? Option B is not the right answer. So the right answer will be option D. So we will see the mechanism. So here NaOMe, so the base will abstract this proton. This will be the most acidic proton, as this is active methylene group. 1,3 dicarbonyl. It will be active methylene group. So the base will abstract this proton, lead to formation of this enolate. And once this O minus is falling back, this carbon-carbon double bond will go and attack at this 1,4 position. Okay. So conjugate addition reaction is taking place here, and this bond will shift, and it will lead to formation of an enolate. Then this will protonate back, and we will get this as the major product. So here Robinson annulation is not taking place, as this is ester. If it was a ketone and there was an alpha hydrogen, there is chance for Robinson annulation reaction to take place. Fine. Is the mechanism clear? Okay. So option D is the right answer. Now coming to question number 5. So this sort of reaction we have already seen. Mukayama aldol sort of reaction. in the presence of silyl enol ethers. So what is the final product of the given reaction occurring via the silyl enol ether intermediate? So this is the ketone we are having, and it is treated with triethylamine and TMS chloride. So we are getting the silyl enol ether, and it is treated with this benzaldehyde in the presence of Lewis acid TiCl4. Okay, option B is the right answer. So we will see the mechanism. So here the silyl enol ether is there, and when it is treated with this benzaldehyde and TiCl4, so the TiCl4 will coordinate with this oxygen of this benzaldehyde, making the center more electrophilic. Then this lone pairs on oxygen will shift here, and this carbon-carbon bond will go and attack on this carbonyl, leading to formation of this intermediate. And then the Cl minus from the TiCl4, it can abstract this silyl group, and this positive charge on the oxygen gets neutralized, and then the minus will attack on this TiCl4. TiCl4 will get regenerated, and the So minus will go and attack on this uh, S, trimethyl silyl chloride, leading to formation of this intermediate. And this upon aqueous workup, it will give this aldol product. Okay, and we have seen that if we are not using this TiCl4, this silyl enol ethers will not react. And the key step is an aldol attack of the silyl enol ether with the Lewis acid complex electrophile. So this is the key step of this reaction. So as you have told, the major product that we are getting is option B. Is the mechanism clear?
Yes, ma'am.
Now coming to question number 6. Which of A to D is the intermediate compound A in the following transformation? So this step leading to formation of A, it is a name reaction. What is that reaction?
Robinson annulation.
Yeah. So this is Robinson annulation reaction. So what will be the A that is formed here?
Option B.
Option B. Okay. We will see the mechanism. So here, as we have seen in the previous slide, for the Robinson annulation reaction, the most important part is an enolizable group on this alpha beta unsaturated ketone. So first, an enolate will be formed here. It will undergo a conjugate addition reaction, leading to formation of this intermediate. And this upon an intramolecular aldol reaction, we will get this final product. So first this enolate is forming, and this upon oxygen upon falling back, this carbon-carbon double bond will undergo a conjugate addition or a Michael addition reaction. This conjugate addition reaction is also known as Michael addition reaction, leading to formation of this enolate, and this can abstract proton, leading to formation of this intermediate. Here the reaction of this enolate is not taking aldol reaction of this enolate is not taking place, as we will be getting a 4-membered ring. Since there is a chance for formation of 6-membered ring, the 4-membered ring formation is not possible. Now we are having this compound, and then an intramolecular aldol reaction. So the base will abstract this proton, leading to formation of this enolate, and this will go and attack on this carbonyl group, leading to formation of this O minus, and this will abstract proton, leading to formation of this aldol product. Now an even CB elimination reaction will take place. So the base will abstract the proton here. It will lead to formation of this enolate, and this upon falling back, this OH minus will be removed, leading to formation of this alpha beta unsaturated ketone. So this is the mechanism for Robinson annulation reaction. So the right option is option B. Now coming to question number 7. Which will be the product of following reaction? So what is the name for this given reaction?
Henry reaction.
Yeah. So the reactions involving nitroalkanes, it is known as Henry reaction. Nitroalkane will be reacting with ketone or aldehyde in the presence of a base, giving what will be the product? Is it alpha nitroalcohol, a nitroalkene, beta nitroalcohol, or beta amino alcohol?
C. Beta nitroalcohol.
Yeah, beta nitroalcohol is the right answer. So we can see the mechanism for Henry reaction. The base will be abstracting this proton, leading to formation of this intermediate. So here this anion will be stabilized as it can conjugate with the nitro group, and this upon falling back, this bond will go and attack on the carbonyl carbon, leading to formation of this tetrahedral intermediate, and it can abstract the proton, leading to formation of this beta nitro alcohol. When we are considering the position of the alcohol, it is beta nitro alcohol. Is it clear? Okay. Now coming to next question. Which of the following is not true about enamines? Enamines are derived by the condensation of an aldehyde or ketone with a primary amine. Enamines are versatile intermediates. Enamines are considered to be nitrogen analogues of enols. Enamines, they are tautomeric form of imines, which is not true about enamines.
Option B. Option A.
Option A is the right answer. So, enamines are formed by condensation of aldehyde or ketone with secondary amines. That is the right answer. So, for enamine formation, we should have an aldehyde or ketone. It should react with a secondary amine. It will lead to formation of the enamines. Okay. So this is how enamines reaction will take place. So first an imine will be forming, then tautomerism will take place, leading to formation of enamine, and this lone pair on nitrogen will fold. This bond will go and attack in a 1,4 addition fashion, and we will get this enolate, and this upon abstraction of proton, it will lead to formation of this intermediate, and upon hydrolysis we will get this diketone. Clear? So here, if it was secondary amine, then it might be right statement. So what is not true about enamines is enamines are derived by condensation of aldehyde or ketone with a primary amine. Now coming to the next question. Which of the following reactions does not indicate the correct main products? So four reactions are given, and you should see the product as well. So which is not giving the correct main product?
Option C.
Option C is the right answer. So we will see the mechanism for each of the reactions. So in the, this ketone in the presence of this dimethyl amine, it will lead to formation of enamine. First this imine will be forming, and then it can tautomerize, leading to formation of this enamine. Now coming to the next reaction. So this enamine can attack on this benzyl bromide in in SN2 fashion, leading to formation of this intermediate, and upon hydrolysis, as it is given here, it will give this compound, this ketone. And in the next case, here the triethylamine is there, so it will lead to formation of this enolate, and it can, this O minus can abstract this SiMe3 from this SiMe3 chloride. So this is the product that will be formed. Okay, so here they have given different answer, so that was wrong. Now coming to the next one, in the presence of TiCl4, this chlorine will coordinate with TiCl4, leading to formation of this TiCl5 minus, and this carbocation will be formed. And then if chloride is present, that will abstract this SiMe3, then this O minus will fall, and this carbon-carbon bond will go and attack on this carbocation SN1 fashion, leading to formation of this product and SiMe3Cl as the byproduct. So when we see, this was the reaction which involved wrong main product. So this is the right answer in question 9. Clear? Any doubts?
No, ma'am.
Okay. Now coming to the next question. Which of the following reactions show a correct main product? So here 4 reactions are given and they have given the product as well, out of which only one reaction is correct.
Option C.
Option C is the right answer. So we will see the mechanism for all of these reactions. So in the first reaction, so here we are having alpha hydrogens. The base will abstract the alpha hydrogen, leading to formation of this enolate, and this enolate, upon falling back, this carbon-carbon bond will go and attack on this ester, leading to formation of this tetrahedral intermediate, and this tetrahedral intermediate, upon falling, this O minus will fall and this OET minus will leave, leading to formation of this alpha beta, sorry, 1,3 dicarbonyl compound. And again there is a proton, so that proton could be abstracted, leading to formation of this enolate, and this upon, here all the steps will be reversible, and this step makes the reaction irreversible, so we will get this compound. So here there is a CH3 as well. Okay, and in the presence of this um, lithium based base, so here, since it is a bulky base, so it cannot abstract the proton from this position. So here steric reasons will be coming into picture. So we will get this as the main product. So here in our question they have mentioned this as the main product. So this is wrong. So here instead of 2 CH2 there will be 1 CH3. So this is also wrong. So this is the main product that will be formed in this reaction. So this amine will be abstracting this proton, leading to formation of this enolate, kinetic enolate. So this is a bulky base. Bulky base will lead to formation of a kinetic enolate. Now coming to the next reaction. So here KH, H minus is the base. So it can abstract the proton from this position, as sterics will not affect, and also here the temperature is 20 degrees Celsius. So this can abstract the proton from here, leading to formation of this thermodynamic enolate. So this is the right answer. Now coming to next question, uh, this OLI, it cannot react with this pH benzyl bromide, like like alkylation reactions are taking place. So this lithium enolate will react with this benzyl bromide, leading to formation of this PHLI and this enolate, and this upon hydrolysis it will lead to formation of this ketone and benzene. Okay, so this sort of mechanism is taking place there. This is benzyl bromide. Consider this benzyl bromide and OLI in our case. So that will attack at this position, or it's sort of reactions involving radical sort of reaction. Okay, so then this will be falling back and this radical will be formed and bromide will add to here. Sorry, lithium will be coordinating here, and this bromide will be coordinating with this our other species. OBR will be forming there. So this sort of mechanism is taking place here, just for making this more giving more clarity to this. I have attached that mechanism. So this is how the reaction is taking place. So since they have mentioned here pH, that was the wrong answer. So the only correct main product is given in option C. Clear?
Yes, ma'am.
Okay. Now coming to question number 11. Which ester will not give a good yield of Claisen condensation product with NaOEP in ethanol? Will not give a good yield.
Option C.
Huh? Option?
Option C.
Okay. Option C is the right answer. So we will see what is the reason behind that. So for the Claisen ester condensation to take place, here this is the mechanism we have seen there. And for making this irreversible, we should have one more proton here, and that will be abstracted, leading to formation of the enolate. So this will make the reaction irreversible. This step is making the reaction irreversible and giving better yields. Now, if you are not having, if the original ester has two substituents on the alpha carbon atom, the formation of the stable enolate of the product is no longer possible, as there are no hydrogen atoms left to remove. So if hello, who is unmute? So if we are having two substituents on the alpha carbon of the ester, then we will get this product, and for further stabilizing the or making the reaction irreversible, there is no proton to be abstracted. So that is why, so this reaction can go back and give the starting materials back. So in this case, here two substituents are there. There will be no hydrogen left for further abstraction. So that is why this product is giving lesser yield for the Claisen condensation product. Clear? Any doubts?
No, ma'am.
Okay. Now coming to question number 12. What would be the starting materials used if the following molecule was made using Robinson annulation? So this is our final product. They are asking what is the starting materials that is used for getting this final product.
Option D.
Option D is the right answer. So mainly we need to consider like if we cut at this position, so here we will be getting COOET, and the other partner will be the uh, alpha beta unsaturated coupling partner. Okay, so we will see the mechanism. So here we are having this as the starting material in the presence of a base. The base will abstract this proton. Base will abstract this proton, lead to formation of this enolate, and this can undergo Michael addition reaction with this alpha beta unsaturated ketone, leading to formation of this enolate, and this enolate will get quenched by abstraction of proton, leading to this product. Then again in the presence of base, this proton will be abstracted, leading to formation of this enolate, and this can undergo aldol reaction, leading to formation of this product. Then upon abstraction of proton, we will get this aldol product, and then it will undergo even CB mechanism by formation of this enolate, and once it is falling back, this OH will be removed and we will get this as a major product. So this was the product that was given to us. So these are the starting materials that is being used. So when so you can work out how we are getting the other what will be the products that we will get upon Robinson annihilation reaction on the other starting materials. Okay, so here I have just given, so this is the starting materials and it will give this as the major product. So you should work out the mechanism for each of these reactions. When these two are used, this is the major product that we are getting, and when this is used, this is the product that we are getting. So this mechanisms you should work out. So this you can consider like a homework. Okay. So here this product we are getting by the Robinson annihilation reaction of these two starting materials. Now coming to next question. The major product formed in the following transformation is. So here first step is like a 1,4 addition, because here we are forming methyl copper species. Transmetallation reaction will be taking place between magnesium and copper, and we will get methyl copper as the major species. So here first 1,4 addition reaction will be taking place.
Option B.
One second. A, B,
No, option C.
D. Actually, alkylation is favored to take place at means carbon center. So D will be the right answer. Okay. So this is the mechanism. We are having the starting material. So methyl magnesium chloride and copper chloride, it will lead to formation of methyl copper species. So this will favor 1,4 addition reaction. So the methyl 1,4 addition reaction will be taking place, leading to formation of this enolate, and this upon falling back, it can, sorry, there is already arrows. This upon falling back, it can add on to this allyl chloride, or alkylation reaction can take place with allyl chloride. Either it can attack at this position or it can attack at this position, both will give the same product. So this is the final product that we will be getting. Mechanism clear na?
Yes, ma'am.
Okay. So this is the final product that we are getting, option D. Now coming to next question. Which of the following is the product of the given reaction sequences? So this is which reaction?
B. AA.
A is the right answer. So aldol condensation reaction is taking place here. So here what is happening? It will be forming, enol will be forming, and then this lone pair on oxygen will fold. This carbon carbon bond will go and attack on this sender. This both are identical. This is symmetrical compound, so both carbonyls are identical. So this will go and attack on one of the carbonyls. We will get this as the final product. Okay, and then this will be the aldol product. Then again enolate can form, and it can lead to E1CB sort of elimination reaction, leading to formation of this alpha beta unsaturated ketone. So option A is the right answer. Any doubts?
No, ma'am.
No.
Now coming to the last question in this series. When aldehydes lack alpha hydrogen is treated with concentrated solution of a strong base, Cannizzaro reaction take place. The plausible mechanism of the reaction is given below. So this is the mechanism for Cannizzaro reaction. So here we are having an aldehyde, and when we are treating it with an alcohol, one nucleophilic addition will take place. It will lead to formation of this intermediate, and this intermediate, it can react with another molecule of this aldehyde. So this is the slowest step in this reaction. Hydrate transfer will take place, and it will lead to formation of this acid and alcohol. Then this then this acid can the alcohol can abstract the take the proton from this acid, leading to formation of this carboxylate and this alcohol. This will be alkoxide first. Okay, so what is the rate law derived for the above mechanism?
C.
C is the right answer. So we will see how we are deriving the rate law. So a rate law shows how the rate of a chemical reaction depends on reactant concentration. For a reaction such as AA give products, the rate law generally has the form rate equal to K into concentration of A to the power N, where K is a proportionality constant called the rate constant, and N is the order of the reaction with respect to A. The value of N is not related to the reaction stoichiometry and must be determined by experiment. So for a reaction given below, AA plus BB gives CC plus DD. So the rate will be written like this. Rate proportional to concentration of A to the power X into concentration of B to the power Y. And if we are bringing a proportionality constant K, so it will be rate equal to K into concentration of A to the power X into B to the power Y. So here A, B, C are stoichiometric coefficients, and we should consider this X and Y. They will be partial reaction orders for the reactants A and B, which can be equal, or it can be different from that of the stoichiometric coefficients A and B. It will be experimentally determined. Okay. And the proportionality constant K is the rate constant of the reaction. So we will consider the concentration of the reactants while calculating the rate law. So here we are and we should consider the slowest step of the reaction while determining the rate constant. So this is the slowest step of the reaction, and these are the reactants. So this is an intermediate. So we should consider the reactants that are giving this intermediate. So two aldehydes and one OH minus we are considering. Okay, two molecules of aldehyde and one molecule of OH minus. So here the rate constant will be K into concentration of aldehyde to the power 2. Here maybe it is already determined that stoichiometric constant is equal to that of the what it is order of the reaction. So here it will be ArCHO to the power 2 into concentration of OH minus to the power 1. So option C will be the right answer. Is it clear how it is coming?
Yes, ma'am.
So the intermediate we are considering the reactants that are leading to the intermediate. So this is all for today's session. If you are having any doubt regarding any of the questions that we have discussed today, or any of the um, or regarding any of the topics that are discussed in this week, you can feel free to ask.
हॉल टिकट क्या रहा है मैडम?
What?
हॉल टिकट क्या रहा है?
I'm not getting your voice properly. Can you type?
यस मैम.
Okay. Whole ticket you can download from that web page, I think. They will send you notification when it is out. Whole ticket is out. Mail will be coming.
ओके मैडम.
Hmm. There are no further doubts. Thank you. We can meet next week. Next week I will be taking lecture on Friday probably. Okay. Thank you.